Hello, everyone, and welcome to another Frenetic Webinar, the monthly event when we discuss about power electronics and magnetic topics. Today, we are going to explore the Frenetic and Maxwell 3D options for an optimal performance. Let me introduce you the speakers of today's lecture. We have on one side Sotiris. You already know him as content creator for our newsletters. And of course, as speakers of our last webinar, he did such a great job that we decided he had to present another one. So here he is. Welcome, Sotiris. And from the other side, we have Alfonso. He is our power electronic engineer in the development team. And today he joined us in order to present this webinar about Frenetic and Maxwell 3D. So before starting with the actual webinar, I would like to remind you all about an exclusive promotion we have in Frenetic in collaboration with Maxwell 3D. When you get a yearly license of Frenetic Online, you will receive for free a 3 months trial of Maxwell 3D. In order to have more information about this promotion, you can just contact us, and I remind you that tomorrow you will receive an email with the link to the recorded webinar of today. So in case you want to know more about this promotion, you just need to reply to that email and we will get in contact with you. So with no further ado, I will leave the floor to Sotiris. Just 1 second, and I will allow you to share the screen.
All right, I think I can do it. Yep, you should be able to see my screen. Yeah, all right. Let's start right away. What do we have here? Okay. So what do we have for today? So for today, we're gonna remember just a little bit of some basic advantages of the LLC topology. Then the plan is to move into a path of deriving the magnetic parameters that we need to input to our design platform. In that case, Frenetic Online, but there's a process, there is a little bit of theory. That's what we're going to cover mainly here in this webinar. And after that, we're going to see the process in Frenetic Online, as well as the Maxwell 3D, where Alfonso is going to guide us through that, and then come back to the presentation really to see some results and compare one against the other, just for to have a closure, let's say. So first things first, what do we have in the LLC topology? The thing is, the basic thing that one has to remember about this topology is that the frequency, changing the frequency changes the voltage at the output. So we keep duty cycles the same, 50-50, either it's a full wave bridge or it's a half bridge, it doesn't matter. The duty cycle is set at 50%. Efficiency is usually very high. 92% might be the lowest case when we have like, if you combine the LLC stage with a PFC stage together, the combined efficiency might be something around 92. If you take a look exactly at the LLC topology, which is half of the story. Usually it's around 95-97% efficiency. And why is that? Because every switch on the primary exhibits 0 voltage switching. Well, we should design to be able to operate at that area, but it's not hard in the LLC topology. And the bonus is that we have 0 current switching at the secondary side. Either this is a full bridge, as you can see here, or that might be 2 diodes in a center tap topology or synchronous rectifiers. It doesn't matter. Whilst you have in the phase shifted bridge, in the phase shifted topology, the secondary switches or diodes experience hard switching. and thus we can see that the LLC has some advantage in the same power levels. So the goal for today is to integrate the two magnetic components of the LLC topology, and that is the external inductor and the transformer. Okay, so how can we design a single component that is going to integrate all of the inductance needed in series as leakage inductance? That is the goal. Okay, so the case study is again 130 watt LLC transformer. We have explored that transformer in the last newsletter, so many of you will be familiar with this transformer, but the interesting part is that we try to copy an existing application note. So in the application note, there was a transformer there manufactured from someone else. So the goal was, the case study was, let's copy that one and let's see the performance of one part versus the other versus Frenetic. But in that case, the magnetizing inductance, the leakage inductance, and the turns ratios were already given to us. Okay, so we will start a bit differently in this webinar, like posing the question, like how can we calculate those three parameters? If we know that this is an LLC half bridge, we are talking about reinforced isolation. The input voltage is 430 volts DC. The output power is 130 watts. It's a center tap topology, 48 volts, 2.7 amps. Free convection, and the output frequency ranges from 70 to 120 kilohertz at max. Okay, so the first step always to a power topology is the PFC stage. And the PFC stage has some specs that we want in order to be able to design properly the LLC stage. Now, the most important spec that we're looking for is actually the lowest voltage and the highest voltage of the PFC. Okay. So here the nominal voltage is around 430. Actually, the more interesting part is the lowest voltage, because the lowest voltage is going to dictate the gain, the maximum gain that the LLC needs to be able to provide in order to maintain the voltage at the output. So where is the problem? The problem is, for example, in a power supply, when there is a dropout, it's not called dropout, my English, it's a brownout condition. So usually we specify a hold up time of 20 milliseconds, something like this, 20, 30 milliseconds. So the bulk capacitance of the PFC is going to dictate how fast the voltage of the PFC is dropping. So from 430 volts, with this capacitor, it's dropping down to 388 volts in a brownout condition. Also, so we have one number here. Also, we should check the voltage ripple that this capacitor is producing, and the voltage ripple at the low frequency. So if we have a 50 hertz scenario, we get 100 hertz rectified low frequency ripple. And this capacitor is actually, well, it's really big, what I've selected here. So it's only given us 4.5 volts of ripple. So actually the lowest voltage is going to be this spec here. So if we design the LLC converter properly, then what we're saying is that if we take the plug off for 30 milliseconds, then the voltage is going to drop to 388 volt, and the LLC will be able to maintain its output voltage constant. Then the power needs to come back up in order for the voltage not to drop below that number, of course. Okay, so setting up the specs is important. And well, then we move to the LLC stage. Now, this is a point of confusion for a lot of people. So when you see application notes describing how you should select the ratios of primary and leakage the magnetizing and leakage inductance, as you can see in the diagram here, specified as LR and LM. Many calculators use this convection, which is M equals the primary inductance divided by the leakage inductance, which the primary inductance is the sum of the magnetizing and the leakage divided by the leakage. Or there are other application notes that use a more simplified approach like this one, which is LM divided by LR, which is exactly what you see right here. We will use these graphs. All right, so every application note that you're going to find is suggesting these to select the turns ratios of primary secondary based on the bulk voltage of the PFC divided by 2 times the output voltage. Again, we're talking about a half bridge design here, okay? And from the primary to auxiliary, we're just replacing the output voltage with the auxiliary voltage. The recommendation is 4.5, but 5.2 was selected actually in the application note. You will see that the effect isn't major. It's not written in stone. It's just going to change the gain a little bit, but this is a good point to have those turns ratios selected like that. And then using those turns ratios, again, the output voltage is known, the back voltage is known. We are assuming half a volt drop in the output diodes for the half bridge LLC and a volt drop at the MOSFETs here. So just for some extra accuracy, you can ignore these as well. It's not going to change much. So the minimum gain that we need is 1.18 and 1.33 is the maximum gain. And here is a better place to take a look at what's happening. So we know the gains that we want, right? Based on the output voltages and the minimum voltages. Okay, so at the minimum voltage, which is 388, the maximum, we need the maximum gain. And that is the maximum gain. Okay, and when I say gain, it's okay. Well, we're gonna see it better here. Okay, then it's time to select the M value. The M is the ratio of the magnetizing versus the leakage inductance. We just talked about this before. Okay, selecting a value from 2 to 6 is the norm. Here was a 3.4, 3.5 ratio was selected. And if you take a look at the graph here we plot here the peak gain that the LLC can achieve versus the quality factor. And the way we work is first we choose the M. So the M is very close to 3.5. 3.5 is this one, the dashed orange line, and then we move up until we find a gain value. In that case is 2.1. That is higher than the highest gain that we already had. So in simple words, we have here 1.33. Usually a good thing to do, always to do, is to give it a little bit of a wiggle room. So add 30% more than that. So that would take you around 1.5. So if I select anything above 1.5, then I'm pretty much covered, as you're going to see in the next slide here. So okay, so you can see the minimum gain 1.18 that we calculated. The maximum gain is 1.33. Actually, if you add that tolerance that I've said before, that would take us right there. Okay, so this is the operating the frequency operating window that we're gonna that we have selected. And you can see 2 curves here. One curve is the dashed curve, which is the no load condition. So under no load, the gain goes up, goes way up. And under full load, you can see that what we have selected here also is giving us a high gain value. So operating in this area is very doable. So the goal is really under full load, this blue line should be higher than the highest gain that I need to get the voltage at the output. Okay, it's as simple as that. So the one thing that we need to calculate before getting into the magnetics and the LC tank is to calculate the AC resistance of the load. Okay, AC resistance, don't let this confuse you. We're talking about the load at the output of the LLC converter as someone can reflect it back to the primary side. So basically, if we know the power at the output, which is 130 volts, we know the turns ratio, we know the output voltage, then we can say that the LC tank that gets formed in the primary side effectively sees a resistance of 319 ohms, and that is enough info for us to specify the series capacitor that we want for this topology. Again, we're talking about here. This is the capacitor that we need to calculate, and the leakage inductance, and the magnetizing inductance, of course. So that's the goal, right? So going back here, the resonant capacitor that we need is 50 nanofarads. The leakage inductance that we need is 175 microhenries. And given the M factor that we set before at around 3.4, we can find that the magnetizing inductance that we want is around 600 micros. And now we're ready basically to do the design. So we have calculated the magnetizing, the leakage, the turns ratios. It's time to go to a FO really. Okay. And then we come back here again. Okay, so just a little thing first. This is the topology. Okay. Half bridge, as we said, 175 micros, 595 micros right here, and 50 nanos of capacitance in series. And we have a center tap topology with an auxiliary winding. Here we have simulated this on our add-on, which is Suzuka Simulator, and it's really easy to play with the frequencies, steady state conditions, and so forth. So we put a 17.7 ohm resistance to simulate the 130 watt load at 48 volt output right there. And we have exported the magnetic waveforms here, which we can do seamlessly, download them and upload them back here to our custom design. Okay, and we have uploaded the waveform. So this is the primary voltage waveform, as seen here, right here, as you can see. So we're specifying the frequency, the inductance, the output power, and the turns ratios, 5.22 and 5.22 for secondary 1 and secondary 2, and the auxiliary winding at 15.6 to get that 15 volt rail that we need for the converter. So waveform. Then we can move on to the core optimizer part of the program, but really this was a copy of an existing design, so it makes sense just to talk about part of the core optimizer really. So we had already selected an ETD 341711 as in the application, and TDK and 97 material was selected there, but we can see that with the core optimizer for the same number of turns, you can choose a better material actually. But again, the goal wasn't to optimize, it was just to see the accuracy of the tool. So moving straight to the core part, we have the TDK N87, the same core as in the application, and 47 turns exactly. And this is the gap that gets calculated to achieve the the inductance that we want. It's not 770, it's 806. I mean, just 10 micros of difference here are 50 microhenries of difference. This is very tricky to do exactly right, but you can get it at the lab, no problem. So you can see here the AC flux swing and the peak flux swing are the same, 185 milliteslas, and the core losses are at 1.72. This is the final iteration number that we get for the losses. And going to the windings, what we had here, we had the 47 turns, as said, one parallel leech wire, 105 strands by 50 microns per strand. And for the secondaries, which are grouped, and this is an important point, let's talk about that in a second. So 9 turns, 3 layers, as you can see here. The secondary and secondary 2 are the power windings, so you can see them grouped, and it's a leech wire of 135 by 70 microns. And the auxiliary winding right here, grouping is important because it's gonna make the leakage inductances of the windings to be as close as possible. Like even 10, we can tolerate 10% difference in the circuitry, no problem. But usually it's better than that. And yep. And always, if it wasn't for the leakage inductances, I mean, the actual inductances of those windings, they should be matched because in a center tap topology, we have to match those things. So taking a look at losses, again from Frenetic, but we're going to check them back in the presentation. You can see that the total losses are around half a watt. Let's go back here and see that. So half a watt is for the winding, and the core losses is around 1.8 watts. And yep, we will talk about the temperatures and so forth after the Maxwell. You can see the pinout here. We got exactly the same. There is no mystery here. And yeah, dataset is bill of materials and so forth. We don't care about that right now. I think, Martina, you can pass the ball back to Alfonso.
Sure, give me a second. Okay, Alpha, you're muted, if you can.
Can you hear me?
Yes, great.
Okay. Well, hello. Now I'm going to explain how we work with the ANSYS tool to obtain the best results. I usually use it as a complementary tool of Frenetic Online, okay? But I'm going to explain how to obtain the results that I'm going to show you directly from the design that Sotir is introduced. So first of all, I have to say that this 3D model, okay, is directly built with the software that we developed. And with that software, what we do is we take one design directly from Frenetic Online, and we are able to build this 3D design in ANSYS Maxwell. So the thing is that we can save a lot of time there in the design process, and also in the material definition process, and also the introducing the excitations and everything. So first of all, as you can see, we have only 1/4 of the whole design. This is because we optimize computational cost and time applying symmetries to the model. Okay, so as you can see here, we have one symmetry applied to the X plane and Y plane. Okay, so then after drawing everything, we make sure that the excitations and everything are all right. Okay, so we have the excitations, direction, and everything. All right. Okay. We can see that the waveforms are directly imported from Frenetic Online, which are the same that Sotiris show you. Okay. After that, we have the mesh operations. Okay. The one thing about the finite element analysis softwares, as you may know, is that you have to define a mesh for obtaining pretty accurate results. You have to have a very fine mesh, or at least a good quality mesh. Developing meshes is quite complex, but we are quite happy with the meshes that our software can produce, because we always have good results from them. And after that, we can define, well, it is already given, but we can adjust our definition, our analysis setup, okay, to have the stop time step, and everything, okay, in order to obtain the results, okay. So in this case, what we do is we simulate 2 period times, and we always take the second one because we assume that the first one is a transient, okay. And we get the results for core losses and winding losses in this case, okay. If you check the winding losses obtained in Frenetic Online, you can see that they are pretty close to the ones that we are getting here in ANSYS, less than 10% of error, even less than 5%, I would say. Then Sotiris will show you. Also the total winding losses. Here we have 0.52. I think in Frenetic Online we were getting 0.53. Okay. Also, the thing is that in ANSYS we normally work with 2 different simulation types. We use the transient simulation to simulate our waveforms. In this case, our current waveforms that are directly imported from Frenetic Online. And then we have a eddy current simulation when we wanna have the inductance matrix, the whole impedance matrix, okay? So I like to have it in these units, and with this tool we can have the DC resistance. In this case, I have it analyzed at 1 Hz, so we can assume that it's purely DC, and self-inductances and mutual inductances that we can use to calculate leakage inductance and magnetizing inductance and everything, okay? Nada. Can you hear me now?
Yep.
Okay. So sorry about that. So I was saying that we have 2 different simulation types. One for analyzing the whole waveform that we are having as an input, and then another one for impedance matrix, which is very convenient sometimes when we want to make sure that our leakage inductance or self inductance is the one we are expecting. So normally all this information can be taken directly from Frenetic Online. That's something that I really like about Frenetic Online. That is that in the same package, in the same tool, we are getting magnetizing inductance, DC resistances, B field estimation, losses, and everything. One thing that I don't quite that I prefer about Frenetic is that you can get everything in the same package. About ANSYS, you need a lot of modules. Actually, for example, when you wanna run simulations in which you want to combine temperature prediction and loss prediction, let's say, you have to have several modules. First of all, you would need this one. We always with Frenetic Online we can provide Maxwell 3D simulations, okay? But in that simulations, you can estimate temperature. For that, you would need the IcePack module of ANSYS. And also, if you want to have, you want to save computational cost and time, you would need the module of high performance the one module of high performance computation. Okay, so we normally think that it's a good option to run ANSYS with Frenetic Online, because here in ANSYS you can analyze the impact of little details. Let's say if I wanna know how the leak inductance is gonna change as a function of the position of all these wires, we can have that information. And also, I think a very good option is the ability to plot the B field, H field, and everything. Okay. In Frenetic Online, for example, one thing that we have implemented is the fringing effect loss estimation. Okay. Our proximity losses are going to be always affected by the fringing effect. Okay. And with ANSYS Maxwell, we can see how that fringing effect is going to look like. So in this case, for example, we can see here that, for example, in this case, the fringing effect is not going to affect our wires. So we are not going to have, or we are going to have very few losses related to this one. Also, a very good thing is that we can have our estimation in the B field, okay? We can have something like this. And also we can check if our B field is the one that we are expecting. For example, in this case, I took the point in which the B field is higher, and we can see that the higher point in the center leg is 185 milliteslas, which is something that we already knew because we had that calculation in Frenetic Online. And I would say that I think that it's a very good combination. The things that you can have with ANSYS, like plotting the fields, H field and B field, is something that we really like when we want to know for example, how are gonna how the gap is gonna affect the whole structure or that kind of things, or which points are gonna can be affected by saturation. For example, we can see here in the corners are kind of saturated, but it's not something that is going to impact our magnetic. And that's it, I would say.
All right. So I think, Martina, you have to give back the access. Just to show one slide.
I wanted to say that in the meantime, if any of you has any question, you can write it in our Q&A section, and we will answer to them at the end of the session.
Okay, can I share? Maybe in a bit. No, I can't share again.
Okay. Let me check again.
Try to flip it. Yep. Okay. And well.
Okay, we see your screen now.
Let's see the last part of the presentation. Okay. Now this is what we have. Well, we have the Frenetic. Oh, we have Frenetic, we have Maxwell, and we have the measured results for a sample that we have constructed. So you can see that the accuracy is pretty high here because the predicted numbers are okay. I might let's bring the pointer out. Okay, so the measured value is 174 microhenries. Well, I'm mistaken here. This is 178 in Frenetic. It's a difference of 4 microhenries. So this was one key point that I forgot to mention, because the usual route to getting the leakage right is trial and error usually. I mean, even the best approaches cannot get exactly right at first go. Here we got it, because what you can see here, this is a 5 millimeter gap between the windings. So there is a significant gap here, and this is pretty accurate. So again, the magnetizing inductance, we wanted something around 600 micros. We got 596. That is pretty okay. And the sum of those is the primary inductance at 770. With Maxwell, we got a slightly different result, because the truth is that if you design, when we made the sample in the lab, like the gap that we needed here for the two core parts is 0.19 millimeters. If you check with Frenetic and you put in 0.2 millimeters, you have more than 50 or 60 microhenries of difference. So that is very likely the reason why there is a difference here in the primary side. Okay, the DC resistances are pretty spot on, pretty similar for both of those, and the measured results are a bit higher than those expected, but again, those are measurements at 25 degrees. When you simulate the actual transformer in Frenetic, those changes, because copper heats up, so these numbers are valid only for 25 degrees, as you can see here. Of course, this transformer was tested, hypo-tested, because we wanted to pass reinforced isolation. Okay, and 4 kilovolts between the two primary, the primary and the secondary side was applied. So shorting all primary windings, shorting all secondary windings, applying 4 kilovolts, 60 seconds AC, which is the hardest, the strictest you can do. This is measured with a leakage current of 60 microamps, which is well below the 1 milliamp threshold that we have set as a pass or fail. And hypo-testing was performed with the primary and the core, and with the secondary and the core, respectively, the same, 2 kilovolts in each case. Again, the same conditions, and you can see here the leakage is even lower as expected. The primary and secondary capacitances were measured at 100 hertz and 100 kilohertz to show the difference is practically the same at 30 pico. This is a very nice thing with LLCs when there is a two-chamber approach here, that the capacitance is really low between the two windings, the primary and the secondary, because there is this large gap here. So this is extra special in particular applications. Maybe not so much in an LLC, but this is always a good parameter to get as low as possible. And the core and the windings at 85 kilohertz, which was the actual operating frequency when we tested the transformer. Again, Frenetic 172 as core losses, 167 from ANSYS, and for the windings we got really close here at 0.53 and 0.52 watts respectively. And something final, again, you have seen that probably in the last newsletters, but just to show you the real thing is right here. This is the transformer under test. So if you take a look at that number up here, this is the green cross. If you take a look at the red cross, this is the maximum measured in each picture. So you can see that, let's take, for example, the windings. At 63 degrees, the windings are at 64 predicted. And the hotspot, again, it's supposed to be the central leg gap. We cannot see that exactly, but if you move closer to the center, let's say from the side, you can see that 65 degrees is about right. Again, there is a plus or minus 2% or plus or minus 2 degrees of difference, whichever is higher from the camera itself. So there is that error over there, but I mean, those are insignificant changes, and this is with natural convection, okay? So this design is pretty okay as it is. I mean, nobody needs to change it. If you're okay with the space that it takes, an ETD 34 core, this is reinforced insulation, temperature is fine. Maybe you could do a little bit better on the core side because you see the core losses are the major driving force, but overall it's the temperature is well balanced. I mean, the windings are 64, the core is at 60. This is a well balanced design anyway. And just for kicks, we had here a forced cooling at 2.4 meters per second, just to see the difference. Again, tested for 1.5 hours approximately until the temperature stabilized really. And you can see that the hotspot is 38 degrees, which is in one picture is 37 in the other. Well, ignore that part. This is not true. This is something else picked up, but this is about right, 38 degrees. Which is that little test over here just to showcase what can you do with Frenetic. And again, this is an oscilloscope picture, and you can see that here we have triggered in the middle, but you see the oscillation happening. That's because there is ripple in the input of the LLC converter. So the frequency is moving up and down to compensate for the voltage ripple. This is the low voltage ripple of the PFC stage. But if that voltage was completely fixed from a PSU, this would be completely fixed to, well, to 85, 90 kilohertz. As you can see here, it oscillates from 88 to 100 kilohertz. And yep, that's about it.
Okay, thank you guys. I can see we already have some questions.
All right, let's see. Okay. Do you consider proximity effect when assessing resistive loss of the windings? Yes, in Frenetic Online, I can show as well. We have the skin losses. I guess I'm sharing right now, right?
Yes, we can see your screen.
Okay. Let's go in here because it's better to show people. Okay, here you have the windings, you have the skin losses, you have the proximity losses, and if the fringing effect is included here to the proximity losses. So the answer is straight yes. Let's go to, sorry. Okay, let's go to another one. Okay, brilliant option for me designing the transformer, but the question is how I consider the turns winding during designing. Okay, if I got it right. So the thing is, there is a starting point with if you follow the webinar, the starting point is what is the PFC doing in the input? So which is the lowest, the highest voltage, and the nominal voltage. So these three numbers, you have to get them right, because in reality it's going to be a PFC. It's not going to be a lab power supply fixed. So to be real, you need to have those numbers right. And then if you follow the process, you're gonna find ballpark numbers for the turns ratios. Okay. Then you have the turns ratios. Following the process, you find the inductances that you need. So exactly the turns that you want to select, it's for example in this transformer, the turns ratio is 47:9. The information that you have from theory is the 5.2, around 5 turns ratio that you want. Exactly why 47 turns and not 57 or not 37? This has to do straight with the operating flux density that you're going to select for the design. You can, as long as you maintain the turns ratio, you can choose a different turns. So there is some, maybe there is actually some iteration. Oh, this turns this number of turns works better for this or for that design, but this has to do with the process of designing the transformer in Frenetic, or if you do it manually, with you selecting the operating flux density. That's the answer there. Okay, let me see if I can answer that one. Okay, hello. Some of the LLC transformers we have designed use 2-chamber bobbins, but the chambers are not 50-50. So the gap isn't exactly in the middle. Is there a workaround when using 2-chamber bobbins that are not 50-50? Since this can have a significant effect on the leakage inductance. So right now in Frenetic, the assumption is done that the gap is in the middle, so it's 50-50, not the gap, but the split bobbin is happening directly in the middle. So you have this much space for the primary winding, and you get exactly the same space for the secondary windings. But something like this, for example, an investigation on that could be done with Maxwell, right, Alfonso? I mean, to make, move the gap, move the not the gap, but the split, not to 50-50, but to 70-30, for example, and see the fringing losses. As Alfonso showed, the fringing losses were in the middle, like if we can say that they were affecting 3 millimeters around the gap. Now, if we moved those chambers, that middle point away, this could directly affect the secondary or the primary, causing excessive losses. Here is a nice point, because the fringing isn't affecting none of the losses. If we take a look at the proximity losses, are very low. Are we going? Okay, I think Martina got that one. Okay.
No worries, I got you covered, so it is.
Well, I'm taking some time because the questions are long enough.
Yeah,
I
I've
have
seen
to
the
focus.
questions. They are really, really long to read, so take your time. In the meantime, Alfonso, do you want to add something to the conversation?
Yeah, I would like to. I have some thoughts that I would like to share with all of you, which is I think that both tools can work pretty well together, because on the one hand, people who don't master the magnetic materials field can use Frenetic Online because it's a super user-friendly tool. I think that from people who don't have the expertise in magnetic components to people who are really experts can design and can get the best of the tool, designing good transformers and inductors that with high performance. On the other hand, ANSYS, as all of the finite element analysis softwares is a complex tool. However, Frenetic Online can help in this because saving all the time of making the design, the 3D models, the putting the excitations and everything is something that can save a lot of time, and also can help to people who are not that skilled also in ANSYS to make the designs more easier. I think that one thing that Frenetic Online has, which is pretty good, is that it is super fast. You can get your results in like this. I mean, in a very, very, very short period of time. On the other hand, like designing with ANSYS the whole component is something that can take days. But like designing it with Frenetic Online, and then if you want to check something with ANSYS, is something that you can do, and it's something that it doesn't gonna take that much. And another benefit that I think that Frenetic Online has is that everything is online, and we run the software in the cloud. On the other hand, for running finite element analysis softwares, you need a good computer with a lot of resources, which is something that we don't always have. So I think that both softwares can work pretty well with each other, and things that you may want to know in deeper detail, like I explained before about the fields and everything, you can have it from ANSYS. But on the other hand, things that are more straightforward or more practical, like how many losses am I gonna have here, or how is it gonna be the inductance here, are things that you can get from Frenetic Online, which is pretty straightforward and easy to have.
Thank you, Alfonso. So Tiris, we go back to the questions.
Yeah, I think he just gave me the time to really think what I want to say, because I don't like to shy away from good questions. Well, let's read the first one. I read in an application note that the transformer for the series resonant converter and LLC is similar. The only difference is the magnetizing inductance, which is higher in the case of series resonant converter and lower for LLC. Could you tell me, please, why? There is the truth is that I can't remember exactly, but there is a big disadvantage. Maybe Alfonso remembers, but the thing is that when you get a transformer and the part of leakage inductance is free in a transformer, like manipulating the spacing between the windings with one component, you have the leakage inductance. Not always. If the power moves up, that two-chamber approach is not gonna be worth it. I mean, the losses are gonna be much more than using two separate components. This is another thing that we must say. It's not a holy grail, two-chamber approach, and that's it. But the LLC has significant advantages. I think, if I'm not mistaken, with the part of the zero voltage switching, as well as it has a really good performance compared to the series resonant topology in general. As far as the I think the dynamic response is different, but there is a big difference there that I can't really seem to remember, because well, it slipped my mind. I don't know if Alfonso remembers the difference, the big difference between the resonant and the LLC, but we will get back to that. It's just the first, in every application note, it's just the first page really that explains the single difference, but it's free. Like to move from a resonant converter to an LLC, if you move the windings apart, you migrate from one converter to the other, and there you have two resonant frequency. The math is getting a bit complex. Like LLC is way more complex than the resonant one. Okay, hopefully I can answer your question.
A few minutes left. Yes, I think you can answer the last question.
And the last one is, well, I'm not sure about the answer there as well, but like any resonant converter, an LLC converter does not fully utilize the input power due to the phase shift between the current and the voltage. In automotive industry, the converter power varies between 3.6 to 22 kilowatt range. This power underutilization might be a huge problem. What is your insight on that? Well, I'm not gonna answer it straight. In a straight manner, because I'm not really sure if I know the answer there, but I can say that with an LLC going up from 3 kilowatts, you're starting to have a very real problem, which is the inductance part. I mean, using ferrites, the usual inductance values that you need is for that low power transformer, it was 770 micros, which is okay. Like the gap was really small, so it was fine, 0.2 millimeters of gap. But when you start raising the power, you need less inductance, which means that you need multiple gaps, or a big gap between the cores, like 5 millimeters, which is going to cause excessive losses. And it doesn't make sense at the end. You can do multiple gaps in Frenetic Online, like splitting the central leg in 3 parts. We have a demo with a 3 kilowatt LLC transformer that performs very well. It's an automotive transformer, by the way, but above that power level, once you're talking about 4 or 5 kilovolts for a single transformer to be able to support it in an LLC topology, I haven't seen this happening, and it's probably due to this thing that with ferrite you need to gap the ferrites a lot to get that low inductance value. And phase shifted full bridges make sense there. Like the advantage of the LLC that there is zero current switching at the secondary, it goes out the window when you're talking about 10, 15 kilowatts. And there is no comparison. So phase shifted full bridge for the win, in my mind, when you move up the power like that. Yep.
Okay, thank you, Sotiris. And thank you, Alfonso, for the great insights of today's webinar. Tomorrow you will receive the link of the recorded webinar in case you want to have a look at it again. And see you all next month with some new topics on power electronics and magnetics. Thank you all for connecting today. And thank you again, Sotiris and Alfonso.
Bye, guys.
Thank you.
Bye.
Bye.